Yes, hello students. In the previous lecture, we had learned how to select the motor rating for the continuous duty load and short-term duty load. Now, in this today's lecture, we shall try to find out how to select the motor rating in the case of intermittent periodic duty. That is, the motor is loaded for the time period TR, running period, and the motor is stopped or disconnected for the time TS. This running period is very small as compared to the heating time constant, and the stopping period is also very small as compared to cooling time constant of the motor. So the motor neither reaches the ambient temperature during the off period, nor it reaches the steady state temperature rise during the on period. So such a duty is known as intermittent periodic duty. So of course, when the motor is not reaching the steady state temperature rise, then the motor will be underutilized if we select the motor of same power rating. So what we can do is that we can overload the motor. The rated power is PR, then we have overloaded the motor by factor K. K is known as overloading factor, such that during the loading period, the temperature that the motor attains is theta max, that is equal to permissible temperature rise. And then when the motor is disconnected, the motor temperature will decrease, and in steady state, during the first cycle, the motor will start from 0 and reach certain temperature rise. In the next cycle, it will be different, and in steady state, the temperature will fluctuate between the minimum temperature theta min and the maximum temperature theta max. We have overloaded the motor such that the theta max, that is the maximum temperature during the cycle, is equal to the permissible temperature rise of the motor. Now recall the equations for heating and cooling period. The heating temperature was like this: theta equal to theta SS is steady state temperature rise, 1 minus e to the power minus t upon tau h plus theta 1 e to the power minus t upon tau h. Theta 1 is the initial temperature and theta SS is the steady state temperature rise, and tau h is heating time constant, and during cooling the value of theta is given by theta 2, that is the initial temperature at which the motor is disconnected, into e to the power minus t upon tau c. So these were the two equations that we derived earlier. We shall use this equation in today's discussion to find out the value of overloading factor K. So during heating, theta is equal to, the equation is like this: theta equal to theta SS e to the power minus t upon tau h plus the minimum temperature theta min e to the power minus t upon tau h. So this is the equation of temperature rise during the heating period or the running period of the motor. At the end of this running period, that is at t equal to tr, the temperature reaches the permissible temperature rise. We have overloaded it such that this temperature is equal to permissible temperature rise. So at the end of duty period or running period, that is t equal to tr, just put t equal to tr here, temperature becomes equal to theta maximum, that is equal to theta permissible. So theta permissible is equal to theta SS 1 minus e to the power minus tr upon tau h plus theta min e to the power minus tr upon tau h, where theta min is the minimum temperature during the cycle. That is the starting point of this cycle. So this is minimum temperature. So this is equation number 1. During cooling, the initial temperature is theta max. So theta max, the temperature will be like this: theta equal to theta PER e to the power minus t upon tau c. So that is the equation during the cooling. At the end of cooling period, that is at this time, that is t equal to Ts, you can write theta min is equal to theta PER e to the power minus Ts upon tau s. Equation number 2. From equation 1 and 2, you can write it like this: theta permissible is equal to theta SS 1 minus e to the power minus TR upon tau h, plus in place of theta min you put the value from equation 2, theta permissible, e to the power minus TS upon tau s, tau c into e to the power minus TR upon tau h. Now just you take this side on left hand side and take common, theta permissible, 1 minus e to the power minus TS upon tau c plus TR upon tau h is equal to theta ss 1 minus e to the power minus TR upon tau h. Now this you can just rearrange this equation and it can be written as alpha plus this can be written as theta ss upon theta per. That's just take it on this side and this on this side. So this equation becomes like this: 1 minus e to the power minus TS upon tau c plus TR upon tau h divided by 1 minus e to the power minus TR upon tau h. Now this theta ss is the temperature rise, steady state temperature rise when the motor is overloaded. So this will be proportional to the losses during this overloaded period. When the motor is overloaded by a factor of k, then the temperature rise is theta ss. So this is proportional to the power loss at the overloaded condition, that is kpr, and that we discussed earlier also. That can be written as alpha plus k square times pv, where pv is the variable loss, alpha is the factor which indicates that copper loss is alpha times pv. So this is the value of theta ss, and theta permissible will be proportional to the losses during the loaded period, during the losses when the motor is loaded to its rated power. So that can be written as alpha plus pv, that is alpha pv plus pv variable loss plus copper plus the constant loss. So this is the case. Now you can just rearrange your terms and you can find this factor k equal to 1 minus e to alpha plus 1 minus e to the power minus TS upon tau c plus TR upon tau h upon 1 minus e to the power minus TR upon tau h minus alpha. Again, if you don't know the relation between the constant loss and full load variable loss, that is PC and PV, that alpha is not known, then you can just assume alpha to be 0 and the equation will be simplified. This becomes equal to 1 and this becomes 0. So the equation will be simplified and you can use the equation like this. So that will be equation when you don't know the relation between full load copper loss and the constant loss. So this is the overloading factor by which you can load the motor such that the motor's full thermal capacity is utilized. So in that way you can decide what should be the rating of the motor for a particular type of application. Again, the value of k that you get, that is overloading factor, you must see what is the maximum current that the motor can carry and what is the maximum torque in the case of induction motor. So that is subjected to that limitation. So in that way you can find out the value of overloading factor for the case of intermittent periodic duty. So that is all for today. Thank you.